Our next speaker will be Andrew Zhao. He's going to continue talking to us about structured learning Hamiltonians.
Okay, great, thank you. Yeah, my name is Andrew. I'm a postdoc at India National Labs. Today I'm going to tell you about this work about structured learning of Hamiltonians for minimal assumptions. You can find this in the archive, this QR code here, and it's going to appear in stock later this year. So let's get into it. Fortunately, Ewan gave us a really great introduction and discussion of what Hamiltonian learning is. So I'll just give you a brief recap for those of you who are just getting in to the session now. Essentially, we're thinking of a Hamiltonian, which is some linear combination of Pauli terms with some weights. And these kind of tell us like interactions, these Pauli terms, and they tell us like how strongly they interact with these coefficients lambda. And the problem is like a really simple learning task. It's you want to learn all these parameters lambda up to some error epsilon, let's say. And in this case, you're going to do it by querying the time evolution operator. So you're given like access to some unknown dynamics of this quantum system, and you want to do like multiple experiments and try to suss out what are these parameters. So like I would say the conventional access model is what was termed in this paper as like discrete quantum control. But of course, this is like the thing that, let's say, experimentalists are most comfortable with doing in the first place. They've been doing it for decades now, which is you're allowed to prepare initial states. You're allowed to evolve by this unknown Hamiltonian. And in between, you're allowed to apply like control operations. You're allowed to use like some, let's say single and two qubit gates to do unitaries to kind of probe the dynamics of this unknown evolution. And you do some measurements, and you want to, back out what are these parameters. So in the structural learning problem, as again Ewan just told us about, we have the same task, but now we're basically not told what these interaction terms are. We are kind of, in this picture I have here, we've lost like the structure. We don't really know. We just have a bunch of particles. We don't even know, what kind of Pauli terms are interacting. And so the question is, can we both learn the structure, both learn the Pauli terms that are in my Hamiltonian, as well as the parameters that, govern how strongly they interact, and of course, to some side error. And we have the same sort of access model. The previous talk we just saw, I would say like kind of formalize this notion. Of course, you could take some of the prior works on Hamiltonian learning and kind of like adapt it into the structured learning setting as well. And one thing I really like about this kind of notion is that it allows us, if you think about this in an experimental setting, like allows us to catch kind of maybe unexpected interactions. Like maybe you have some model for your Hamiltonian in mind, and you run this Hamiltonian learning algorithm. With structured learning, you can kind of catch like, oh, are there some unexpected terms that are floating around in my Hamiltonian that I didn't necessarily anticipate. So the previous talk, we learned a lot about like these k-local Hamiltonians. We heard a bit about how they can kind of extend beyond k-locality. But I would say like ultimately, a lot of these algorithms, if you really want to apply them, let's say in a purely kosher way, let's say, to do structured learning, it seems to somehow hinge on like k-locality. In some sense, you can just argue that, well, if k is constant, there's like a polynomial number of terms in Hamiltonian. And so, in the most naive case, you can just brute force search over all of them. But you might want to consider that some Hamiltonians that don't necessarily have like necessarily k-local terms. So one thing you might consider is that maybe your Hamiltonian is actually L-local for L is bigger than k, and you don't actually know what L is. This might be a thing to consider. Or you might consider that you have, maybe your Hamiltonian is all k-local except for one term. That one term is like horribly non-local. Something like this might show up in an experiment, or it might show up in like other applications of Hamiltonian learning, like device or algorithmic certification. In either way, we're interested in just considering like how far does this idea of structured learning really extend. So you might think this just in a purely theoretical sense, like if I'm giving you some what I call a sparse non-local Hamiltonian, so really just any Hamiltonian that has at most polynomial number of Pauli terms, but each term is allowed to have like unbounded support. Basically, it's allowed to interact on up to all of the qubits. Is this task still efficiently learnable? And of course, by efficiently, we mean like in polynomial time, both the sort of number of queries to the unknown system and also the amount of computational time you take. So it turns out the answer is yes. This work we show that efficient structured learning is indeed possible for any of these sparse non-local Hamiltonians. And we give kind of two algorithms to do this. So one is kind of using what we call time reversal access. So if you're given access not only to e to the IHT, but also like, let's say, t can be both positive and negative, then we give like sort of this nearly Heisenberg limited algorithm. And the idea is that the evolution time is 1 over epsilon scaling with error, and the computation time is like polynomial in the parameters. But even if you don't have time reversal access, which is, let's say, a pretty uncommon sort of access model in most experiments, you can still do this algorithm with some modifications given just for time access. And here, like the polynomials are a bit worse. You get some overhead, but it's still all like efficient in the sense of polynomial scaling. This is really cool. I would say that the prior work didn't really show like how this is actually possible with like, you're essentially searching over like a space of exponentially many Pauli terms, and you're trying to find like some small polynomial-sized subset. And so the best prior algorithm that I could come up with was based off of this work by Matthias Karl, and essentially like you could actually use that algorithm to show like polynomial time, say queries or evolution time to your system, but the best way you could kind of suss out what are the structure to this algorithm is just by doing an exponentially big computation. You just essentially brute force check over all possible terms, which is like 4 to the n, right? So this, the algorithms that I'm going to present give you a way to basically circumvent that. You don't have to brute force check over every term. The algorithm is based off of this work in 2023 by Juan Castaneda and Nathan Wiebe. And it was really, I'd say, like, kind of flew under the radar a bit. They introduced this idea of a pseudo-choice state. So the pseudo-choice state is this funny little state here where you can think of like the Hamiltonian acting on the Hamiltonian and the identity acting on like the maximally entangled state. That's what this omega is. And so you might think this is not, it looks like a choice state because you have like some n-cubed operator acting on this maximally entangled state. But the Hamiltonian is not like a CPTP map or anything, so it's not really like a choice state per se. And furthermore, I call this like a pseudo-choice state with reference. So you see there's also this reference term, and that'll be important later. But anyways, they propose this state, and they say, well, if I can reduce my learning algorithm to just learning copies of this state, then I can learn the Hamiltonian. You might ask, well, first of all, how do I even compare this state? Okay. It turns out they use like techniques from block encoding, actually. I think in a quite interesting and novel way. Basically using this unknown Hamiltonian, this unknown unitary dynamics, and constructing like block encodings of the Hamiltonian that's up, being dynamically generating this thing. And the circuit looks something like this. But the point is, there exist ways you can use like kind of QSVT type algorithms, like the quantum singularity transformation, to produce this block encoding. You need like, however, controlled access to both the forward and backwards dynamics of this unknown unitary. So it wasn't like the most like practical, let's say, an experimental setup. But if you assume you did have this, so here we need to like actually renormalize things by this delta parameter, which is, you can think about just basically the size of the norm of the Hamiltonian in order to have proper block encodings. But let's say if someone did hand you this pseudo-choice state, what could you do with it? And what they show is that you could do what's called like decoding. So essentially you can define these like funny, like non-Hermitian operators, which look something like this. But the main takeaway is that they're specifically designed such that with respect to the pseudo-choice state, their mean values give you exactly the parameters of the Hamiltonian you want, up to some normalization factor. And so this delta normalization factor is something I could choose. It's the parameter I choose in my like learning algorithm, so that's fine. But this n is like this normalization of this pseudo-choice state. It depends on like the norms of the Hamiltonian and all this stuff. It's kind of complicated, and so in general, like you can't really learn it. That's exactly why they have this like reference state. They have this like reference part in the superposition. It allows them to define like another operator, which lets them learn this normalization factor. Okay, and basically with all this information, you can learn the normalization factor. You can learn these parameters. And actually, you can learn it pretty efficiently in the sense that you can run things like classical shadows to learn like a large collection of observables using just like a few queries to the system. And so overall, the evolution time that they need to get like, say, epsilon error and all the parameters is something like the norm of the Hamiltonian over epsilon squared up to some log factors. So yeah, the pros of this is that we can basically learn like m parameters, let's say, with like log m scaling. This is because like the classical shadows argument. And there's nowhere here that I say anything about dependence on locality. Like our EAs, our Pauli terms, showed up in like their decoding operators, but those are the things that we just like kind of we classically do. We do classical post-processing, to figure out what their expectation values are. The constants, of course, is that it requires, not only controlled forms of your unitary dynamics, but also like time reversal. It needs you to go forwards and backwards. And this is because it's applying these like QSVT type techniques. So that's one con. It's a big con. Another one is that essentially it doesn't support like structured learning of sparse non-local Hamiltonians. The way you can see this is just that like there's no clear way in which you have to define these decoding operators, right, for each E sub A. But if I don't know what they are, then essentially you have to define them for every single Pauli and just brute force check. This is another way you'd have to do brute force checking. So the question is, of course, can we essentially short these cons and turn this algorithm into something that is like polynomial time in all these parameters and get rid of these like controlled time reversal operations. So the first step is to remove the controlled operations. Turns out like this is actually something that's been kind of studied in the literature already, and so we more or less like borrowed this technique and kind of tighten up some of the error analysis. But the main idea is this like controlization technique. It allows you to take an uncontrolled unitary and use the fact that you can not only apply like e to the minus IHT, but really you can apply e to the minus IHT over n for some like large n, let's say. And so the fact that you can break up your time evolution in this way, and you can insert say these control Paulis, allows you to get this sort of equivalence up the global phase. And so it's actually a really cool technique. Suffice it to say that every instant that you use controlled U, say to prepare that block encoding to produce that pseudo-choice state, you can replace with this sort of controlization circuit. And so this will have some polynomial cost in terms of the like the number of times you need to do this randomization step. But you can get like some, you can basically control how closely you want your approximate controlized unitary within some like gamma error. And the really nice thing in terms of looking at total evolution time is that you're basically breaking up a time t evolution into like t over n steps of t over n. So you actually don't get any difference in the total evolution time, but you do have to get like a smaller time resolution per query to your time evolution. And essentially this works by like Pauli twirling and like Q-drift arguments. That's kind of all I'll say here. It's a pretty straightforward derivation though. Okay, great. So let's go back to the slide. If we just kind of plug this in and like, cross our I's and dot our T's, dot our I's and cross our T's, we can remove the need for controlled operations. That's great. The next question is, how do we do structured learning? So without incurring this exponential cost. And so what I'll do here is I'll introduce a second variant of the pseudo-choice state, which I call the reference list. Now this is a pseudo-choice state that's like, it has this h tends to I on the maximally entangled state, but I don't have this reference. And the reason I'm going to do this is because if you kind of expand this state, you'll find that you basically just get like these Pauli basis type terms whose weights are proportional to the parameters in my Hamiltonian. And so actually, I can sample in this basis, in like this sort of Bell basis, these E sub A states, using the Choi-Yamakowski isomorphism. And essentially, it's just like Bell measurements across like the two registers. So using the same sort of ideas that I used to prepare the pseudo-choice state with a reference, I just throw away the control qubit, and I prepare this reference to state, and I do Bell sampling on it. And Bell sampling basically tells me that I can learn with probability proportional to how large that strength is, I'll pick up that element. And so basically there's like two conditions, right? Like one, either the parameter is already really small, it's less than epsilon, in which case actually setting it equals 0 is already epsilon good approximation. So I just do that for the small ones. And I'll just kind of sample this thing until I see the big ones. It's kind of like a coupon collector argument, but I only care about like the common coupons, right? And so basically you can do analysis and show that you can basically sample this thing repeatedly with Bell measurements and get something like the size of lambda squared over epsilon squared, copies of the pseudo-choice state suffice to kind of learn all these labels of the Pauli terms. And this like lambda norm is like, you can think about it as proportional or related to, let's say, the norm of the Hamiltonian itself. Okay, so this is essentially the way that we do structure learning, actually. Let's say structure identification. We're going to prepare this referenceless pseudo-choice state, and we're going to do Bell measurements, and we're going to just essentially statistically pick up like what are all the large terms in my Hamiltonian. And this kind of tells me it for free. And then finally, we want to get rid of this, time dynamics, or time reversal access. So the techniques they use to do block encodings and all these fancy tricks required you to have U dagger. It turns out, actually, shown this in our paper as well, you can also extend those ideas using some of the similar bootstrapping ideas that we heard in the previous talk to get like nearly Heisenberg scaling using like kind of even more QSVT tricks. I won't talk about that here. Instead, what I want to talk about is just like, if I restrict myself to only having 4 time dynamics, can I still like block encode H essentially? This is like the central requirement in order for preparing all these like types of pseudo-choice states. And so yeah, if we can do this, then we would bring our algorithms like axis model in line with sort of the conventional axis model. And it turns out you can do this. It's a bit like, let's say, interesting that it hasn't been done before, but there are perhaps reasons for that. But suffice it to say, you can appeal essentially to the matrix logarithm. So the matrix logarithm is this series here that converges uniquely. Let's say if your Hamiltonian norm is bounded by something. And I can actually just look at this expression, and I can rewrite it into a linear combination of unitaries. So say I pick some integer k, I truncate it to order k, and I can actually just implement this thing, this matrix logarithm, as an LCU. Of course, like all these control things you see down here in this circuit diagram are replaced by those controlization circuits, right? So I don't have an issue with that. And of course, the main thing is that this only requires me to have access to the forward dynamics. I only need U here. There's no U daggers. So you do pay some overheads. You pay some overhead in terms of needing some ancilla. Actually, the amount of ancilla you need is really, really modest. It's like double log in like the size of the Hamiltonian norm. So that's really nice. But you do pay a factor basically in this like LCU norm, which affects like how reliably I can, say, produce this the state that I want. But nonetheless, these are still like polynomial-sized overheads. And so I can use this matrix log LCU to block encode my Hamiltonian. And with that block encoding, I can prepare all of my favorite pseudo-choice states. And in none of this algorithm did I need the time reversal of U. So yeah, so the matrix log lets me incur only polynomial overhead. I can do this structure identification using some polynomial amount of copies. And I can just learn the parameters using that pseudo-choice state method with the decoding operators, again, with the same complexity. Yeah, so this shows up the very last section, the very last con to the pseudo-choice state method. So I'll kind of summarize over here. We give a polytime algorithm for both learning and any sparse non-local Hamiltonian, which basically means like identifying from a pool of like exponentially many terms, just the polynomial number of terms that exist in Hamiltonian. This is achieved quite interestingly by using like quantum simulation techniques, which I think is a pretty neat, nifty like application of quantum simulation techniques. It's not necessarily like a practical way to do it, I would say, but this is more sort of like putting a theoretical upper bound on the hardness of this task. And yeah, like despite the fact that we use like these like QSVT type techniques, it turns out you can get away with just 4-time technique or 4-time applications of your evolution. So open question I'd list would be like making this actually practical. There's very recent work within like the last week or two that suggests like a way forward to making a more practical algorithm that does structure learning for these like non-local Hamiltonians. So that's something to look into. I think it's interesting to ask like what can we do with structure learning of Gibbs states. I think like it's still, at least to me, an open question, like applying this sort of idea to like the static learning axis model. And then finally, I think this matrix log block encoding was like kind of nifty, and I'm curious to see if there's like some utility of using it like in other applications, maybe not even necessarily related to learning. So thank you, and check out the paper if you're interested.
Do we have any questions?
Yeah, thank you for the excellent talk. I'm kind of curious, have you thought about the situation instead of the parameters being constant, them being time dependent? And also, have you thought about the potential of, for example, learning the Hamiltonian and the collapse operator simultaneously?
For the second part, the Hamiltonian and what operators?
Oh, the Hamiltonian and the collapse operators in the master equation?
Oh. Okay, so to answer your first question, no, I've not thought about time-dependent parameters. I think it'd be pretty interesting, yeah. I don't see necessarily what would stop us from doing time-dependent Hamiltonian learning, but I think we need to kind of revamp our techniques. As for like, if you're thinking about like sort of open system dynamics and learning from that, I'd say there's a decent number of works that study just like, say, learning Lambdadians, and some works that do like an overlap in terms of like their study, like learning, dynamics from like a very general perspective. So there are works out there that do study like these open system dynamics. I think applying our techniques, this one specifically, is probably not really feasible since like we very much rely on unitarity. But I don't see a reason why you can't like generalize it, yeah, using some of these other techniques that already exist.
Hi, thank you for the very nice talk. My understanding is that your algorithm need to use ancillary qubits to do the learning. And
right.
I'm curious, is ancilla like necessary for this, or is there any possibility to like remove ancilla to reach the same scale?
Yeah, I don't think ancillas are necessary even for like this most general sparse non-local case. There is work by, I forget all the authors, apologies, but I know Francisco Gutierrez is on it. And they consider like a way you can do structural learning of these sparse Hamiltonians, even without ancillas. Of course, as you imagine, you pay a bit of overhead when you remove the ancillas. But it should be possible, yeah.
Hi, thanks for the nice talk. Could you comment on the prospect for like testing structures of Hamiltonian, and how much better can that be compared to, say, learning algorithms? Let's say testing like underlying graph structure, or maybe even the algebraic structure of terms.
What do you mean by testing the structure, I suppose?
Let's think of the graph as having like the interaction graph, and you might want to test whether it has certain properties or not.
Yeah, so testing, property testing of Hamiltonians is also like a pretty widely studied field now too. I'd say that it's kind of developed in parallel with learning Hamiltonian learning. I guess what I'll say is that it seems like a lot of the techniques that you use for learning definitely apply to the testing case. I think for the sparse case as well, there's been some recent work for testing sparse Hamiltonians. And I think the very high level philosophy is the same, that like these techniques that you use to learn can also be used in like sort of a slightly modified way to do testing as well.
Yeah, thanks for the nice talk. I got a quick question about the way you define the log function.
Yeah.
Because you're defining this for general matrix, and from some maybe remote knowledge of complex analysis, when we define the logarithm function of a matrix, shouldn't we define the branch cut first?
Yeah, I mean, implicit in that definition, or that series definition, is like we've chosen a particular branch cut. Yeah.
But if the Hamiltonian actually is a round branch cut, then there might be a discontinuity of the object you learned.
Yeah, so you have to assume that the Hamiltonian norm is like particularly bounded. There's like this, the norm being bounded by log 2 is what suffices for this series to converge uniquely. Yeah.
But the branch cut is one line starting from the origin and goes to infinity along certain direction. Even for this range, say h norm smaller than log 2, I think there's still an intersection between the branch cut and the domain.
I'll have to think about that. Okay. My understanding is that like just taking this out of like a standard like matrix Lie algebra or matrix Lie group book is that this is pretty uniquely defined. We can talk afterwards.
That's all we have time for. We'll be back in 5 minutes.